Hello once again. In the last class, we talked about Colorau's law of electrolysis. In today's class, we'll be doing Faraday's law of electrolysis. As I told you in the last class that in today's class, we'll be doing this and we'll be starting the electrochemical cell. First, we'll see what this Faraday's law of electrolysis is. Now here I'm showing you electrolytic cell. In this electrolytic cell, I've got sodium chloride and I'm carrying out the electrolysis of sodium chloride. When I dissolve this sodium chloride in water, on dissolving in water, it will break up into its respective cation, that is Na positive, and its anion, that is Cl negative. Now what will happen at cathode? Cathode in this case is negative terminal, the terminal towards which the cations will move. So at cathode, what will happen? The Na positive will gain electron and will get converted to Na. Likewise, if I talk about anode, at anode, reverse will happen. 2 moles of Cl negative will lose 2 moles of electron and they will get converted to Cl2. So this is what is going to happen at cathode and anode. Now from here it is quite clear that 1 mole of Na positive will combine with 1 mole of electron to give you 1 mole of sodium. The molar mass of sodium is 23 grams. So we can say that 23 grams of sodium will be obtained from 1 mole of electron. The charge on 1 electron is 1.6 into 10 to the power minus 19 coulombs. And when I am saying 1 mole of electron, that means it is 6.023 into 10 to the power 23 electrons. That comes out to be 964,800 coulombs. We nearly consider it as 96500. This is 96480, not 00. 96480 coulomb. So that is nearly equal to 96500 coulombs. 96500 coulomb, we call it as 1 Faraday charge. So here in this case, what I can say that 1 mole of electron or 1 Faraday charge is giving me 1 mole of sodium, that is 23 grams of sodium. So 23 grams of sodium is obtained from 1 Faraday charge. Now we'll see Faraday's law, first law. According to first law, the mass of a substance deposited on any electrode is directly proportional to the charge flowing through the cell. That is, the weight of a substance deposited is directly proportional to Q. I give you example for that. Now in the above example, if I'll pass 1 Faraday charge, I'll get 1 mole of sodium. That means 23 grams of sodium. However, if I pass 2 Faraday charge, I will get 2 moles of sodium. That means 46 grams of sodium. So according to first law of Faraday's, the amount of a substance, the weight of a substance deposited is directly proportional to the charge flowing through the cell. The charge can be stated as the product of current into time. Here in this case, the current has to be in amperes and the time has to be in seconds. So according to first Faraday's law, the weight of a substance deposited on any of the electrode is directly proportional to the charge flowing through the cell. The charge is always the current into time. The current is in amperes and the time is in second. Now I'll give you another example. Suppose I have got some cells, they are connected in series. When I am saying they are connected in series, that means same current is passing through them for the same time interval. That means same charge is passing through different cells. And these different cells, they have different electrolytes. Suppose in the first cell, I have sodium chloride. So at cathode, I will have Na positive. In the second cell, I have calcium chloride. So at cathode, I will have Ca2 positive. In the third cell, I have got aluminum chloride. So at cathode, I will have Al3 positive. AlCl3, that will break up into Al3 positive and 3 moles of Cl negative. Now when I am passing same amount of charge in all these three cells, these substances they'll not be deposited to the same extent. Although the first law says that the weight of a substance deposited is directly proportional to the charge, the second law says that if you pass the same charge through different electrolytes, the amount of a substance deposited is directly proportional to its equivalent mass. For example, if I pass 1 Faraday's charge, that is 1 mole of electron, they will give me 1 mole of sodium. 1 mole of sodium means 23 grams of sodium. On passing 1 Faraday charge, I will get half mole of calcium. Now the molar mass of calcium is 40, so I will get 20 grams of calcium. On passing 1 Faraday charge, I will get 1 by 3 moles of aluminum. The molar mass of aluminum is 27. So in this case, I will get 27 divided by 3, that is 9 grams. 9 grams. I would like to tell you one thing, that all these masses, they are the equivalent masses of these very substances. That is, the equivalent mass of sodium is 23, the equivalent mass of calcium is 20, and the equivalent mass of aluminum is 9. Equivalent mass in terms of electrochemistry, we can say it is the molar mass divided by the n factor, that is the valency. The valency of sodium is 1, that of calcium is 2, and that of aluminum is 3. So 23 divided by 1 is 23, 40 divided by 2 is 20, and 27 divided by 3 is 9. Or we can say equivalent mass is the mass of a substance deposited when 1 Faraday charge is passed through it. So here you will see. So according to the second law, the mass of a substance deposited is directly proportional to its equivalent mass. If we join these two laws, we generally get an equation, that is weight of a substance deposited during electrolysis is equal to Z into I into T, where Z is known as electrochemical equivalent. This is constant for a substance, and for different substance it has different values because it depends on the equivalent mass. This Z is actually equal to the equivalent mass divided by 96500. So we can say the electrochemical equivalent is the amount of a substance deposited when a current of 1 ampere is passed through a cell for 1 second. Different substances will be deposited to the different extent, so they will have different value of their electrochemical equivalent. And this is all about Faraday's law of electrolysis. With this, we have finished up with the electrolytic cell. Now we'll move on to the electrochemical cells, and we'll see what electrochemical cells are. Well, electrochemical cell is an apparatus that converts chemical energy into electrical energy. In your 11th standard, you have done the redox reaction. All electrochemical cells, they use these redox reactions to produce electricity. Here, one of a highly reactive metal displaces another metal which is slightly less reactive. I give you one example for this. Suppose I take a container, and suppose this container has got copper sulfate. I am putting a zinc rod into this. This is, say, a zinc rod, and it is dipped in CuSO4 solution. When I am saying copper sulfate, CuSO4, that means I am talking about Cu2 positive ion. CuSO4 automatically means Cu2 positive ion because it contains Cu2 positive ion. Now zinc is more reactive than copper, so it can easily displace copper. The reaction which will occur is Zn plus CuSO4 will give you ZnSO4 plus Cu. ZnSO4 plus Cu. Now we know very well that sulfate ion is always 2 negative. So on the product side, if sulfate is 2 negative, that means Zn is 2 positive. Likewise on the reactant side, if sulfate is 2 negative, copper is 2 positive. If I cancel out the like ions from both the sides, that is the sulfate ion, if I cancel them out from both the sides, the equation I will get is Zn plus Cu2 positive will give me Zn2 positive plus Cu. In this reaction, if you'll see, you'll find that zinc is losing electrons. So zinc is undergoing oxidation and copper is gaining electrons. So copper is undergoing reduction. The question comes to our mind, if it is possible, if we can do one thing, that we take two different containers and in one of the container we carry out oxidation, that is loss of electron. That container will donate electron and it will become negatively charged. So that will act as a negative terminal. And if we get another container where reduction will occur, it will have a tendency of gaining electron. So if it will gain electron, it will become positive terminal. If somehow we can do this thing that we can separate these two electrodes, these two processes in two different containers, one of the container will start acting as a negative terminal and another one will start acting as a positive terminal. So it will become possible for us to prepare a electrochemical cell. Based on this, the first electrochemical cell, that is the Danel cell, was formed, and it basically uses this reaction. We'll see the functioning of a Danel cell. A Danel cell consists of two electrodes. Here I am showing you how it functions. Suppose this is one container I have got, and here another container I have got. In the first container I have got a zinc rod, and this zinc rod is dipped in ZnSO4 solution. ZnSO4 solution. On the other end, the other container, another container, this container contains a copper rod which is dipped in CuSO4 solution. So what will happen at the zinc electrode? The Zn atoms, zinc atom, will lose electron on the electrode and they will come into the solution as Zn2 positive ion. The solution already contains large number of Zn2 positive, so some more Zn2 positive they will come into the solution. So we can write the reaction which will occur here is Zn will give you Zn2 positive plus 2 moles of electrons. My dear students, since zinc atoms, they will lose electrons on the electrode and they'll become Zn2 positive, they'll come into the solution. That means the rod will become richer in electrons. It will get more and more electrons. So the rod will acquire a negative charge. On the other end, what will happen on the copper side? Reverse. CuSO4. When I am saying CuSO4, that means large number of Cu2 positive ion. The Cu2 positive ion will attack on the electrode to gain electrons. So what will happen here? Here reduction will occur. Cu2 positive plus 2 moles of electron will get converted to Cu. More and more Cu2 positive ions will attack on the electrode. They will gain electron from the electrode. They will get deposited on the electrode. They will get discharged. When they are gaining electrons from the electrode will become deficient in electron. Deficiency of electrons means positive charge. So this electrode will acquire a positive charge. So likewise, on one of the electrode where oxidation is occurring is acquiring a negative charge, and the electrode where reduction is occurring is acquiring a positive charge. If we connect both these electrodes through a wire and connect it to a galvanometer, the needle of the galvanometer, I'll show you here, the needle of the galvanometer is always in the center. You have a reading 0 here, then you have reading 1, 2, 3. Likewise on this side also 1, 2, 3. The deflection of the needle shows you the direction of flow of current. Now what will happen? The electrons, they will start flowing from the negative terminal to the positive terminal. But the current is always said to flow from the positive to the negative. That's why galvanometer will show some deflection. And so we'll come to know that the current is flowing through the wire. The electrons, they are moving from the negative terminal to the positive terminal. And this is how this cell works. Well, As far the part of cell is concerned, after some time, the container where oxidation is occurring, that is the zinc container, will become richer in Zn2 positive ion because it is gaining more and more Zn2 positive. So the solution over here will become richer in cations. Whereas if we talk about the container of reduction, that is the copper electrode, the Cu2 positive ion, they are getting discharge on the electrode. So it will become deficient in cation. So on the positive terminal, the solution in the positive terminal will have more number of anions. The solution in the negative terminal will have more number of cations. In order to maintain internal circuit, in order to maintain ionic equilibrium, we use a U-shaped glass tube. This glass tube is like this. It is often fitted with glass wool on its mouth. On the two openings, it is fitted with glass wool so that the content which is inside should not come out. And in this, we generally put potassium chloride plus gel. In the semi-solid state, we put a paste of potassium chloride. The function of salt bridge, this is known as a salt bridge. The function of salt bridge is to maintain ionic equilibrium. It absorbs anion from the container where they are more and it delivers them to the container where the anions they are lesser. So it maintains ionic equilibrium and internal circuit. This is how the cell functions. Now comes the representation. If we want to represent this cell, how we can represent it? Well, in that case, I can write Zn, single line, Zn2 positive, C1, double line, Cu2 positive, C2, single line, Cu. This is how we represent a cell. On the first part, we write down the oxidation part. And in second, we write reduction. Well, what oxidation is showing? It is showing that Zn is getting converted to Zn2 positive. Zn2 positive means ZnSO4. And the concentration of that ZnSO4 is C1. So you'll get a value here. In this bracket, in this parenthesis bracket, you'll get a value like 0.1 molar or 0.001 molar, 0.02 molar, something like that. Likewise, the second part shows Cu2 positive ion. That means CuSO4, whose concentration is C2. Here again, you will get some value is getting converted to Cu. And both these containers, they are connected together by a salt bridge. So these double line, they represent salt bridge. There are lot of different type of cells we have where the two containers, they are joined together by different phases, by different means. It's not always that salt bridge connects these two containers. So it's not always that we have double line between them. Like in concentration cell where the difference is just because of the difference in the concentration, we generally put dots like this. That means the two containers, they are connected together through concentration difference. Anyways, that's not there in your syllabus. This is how we represent a cell. And this is how Danel cell functions. Now the other question comes to our mind that if we have a look at the reading of galvanometer here, suppose galvanometer is showing a reading of 3 volts. In this arrangement, suppose the reading which galvanometer is showing is of 3 volt. That means lot different type of combinations, infinite number of combination. It means the negative can be -1 and the positive can be +2. The negative can be -1.5, it can be +1.5. So you will get infinite number of combinations for that. The question comes to our mind, how is it possible that we can know how negative the negative is and how positive the positive is? Well, yes, it is possible. I'll tell you how we can do that. We can calculate how negative the negative terminal is and how positive the positive terminal is, because once we'll know that, we need not to have galvanometer to know the potential difference between these two electrodes. Like here we are using the galvanometer. Galvanometer is simply telling me the difference of potential between the positive and the negative. But once I know how much positive the positive is and how much negative the negative is, I need not to have the galvanometer. Without galvanometer, I can do that. The question comes to our mind, how we can calculate how negative the negative is and how positive the positive is. First, we'll see what we call it, how positive the positive is and how negative the negative is, what we call it, what term we use for that. Well, the term we use for it is electrode potential. It is electrode potential. And we'll see what this electrode potential means. Here I would like to show you an electrode, like we talked about the zinc electrode. We'll talk about that. Now suppose this is the zinc electrode, and this zinc electrode is dipped in ZnSO4 solution. This is the ZnSO4 solution, or we can say Zn2 positive solution. Now what will happen at this zinc electrode? The zinc electrode will undergo oxidation. The reaction will occur. Zn will get converted to Zn2 positive plus 2 moles of electrons. So zinc atom will lose electron on the electrode. They will get converted to Zn2 positive. They will come into the solution. So you'll get more and more number of Zn2 positive ion into the solution. As the solution will start acquiring the positive charge, the rod will start acquiring the negative charge. A situation will come when you'll have an equilibrium. When the solution will get saturated with the cations, it will have maximum number of cations. It will get cations which maximum which it can accommodate. When the solution has got maximum number of positive charge, that means the rod has got maximum negative charge, because these Zn ions, Zn atoms, they are losing electrons on the rod, they are getting converted to Zn2 positive and they are moving into the solution. So more and more electron they'll get accumulated on the electrode will become negatively charged. Now an equilibrium will get established. Suppose the solution can accommodate maximum of 50 Zn2 positive ion. That means now the 50 Zn2 positive ion, they have come into the solution. Now when 50 Zn2 positive ion, they have come into the solution, that means 100 electrons are there on the electrode, because every Zn loses 2 electrons to become Zn2 positive. Now an equilibrium is established between the electrode and the solution. Now if a single Zn will get converted to Zn2 positive, some other Zn2 positive will get discharged. That means the charge in the solution, the positive charge in the solution has become constant, and the negative charge on the electrode has also become constant. So now we'll see a potential difference between the electrode and the solution. Between the electrode and the solution, there's some potential difference between the electrode and the solution. This potential difference is known as electrode potential. So I'm telling you what electrode potential is. Kindly remember this, or if you want to write it down, you can write it down. It is the potential difference developed between an electrode. Here in this case we have got zinc electrode. It is the potential difference developed between an electrode and the solution in which it is dipped. Here in this case we have got the solution of ZnSO4. So the solution has to be capable of donating the same ions as that of the electrode. You cannot put zinc electrode into copper sulfate. If you have got zinc electrode, it has to be dipped in ZnSO4. So it is the potential difference developed between an electrode and the solution in which it is dipped. And the electrode and the solution in which it is dipped should be capable of donating the same ions as that of the electrode. So it is the potential difference developed between an electrode and the solution in which it is dipped, and the solution should be capable of donating the same ions as that of the electrode. If oxidation occurs on the electrode, as in this case, we call it oxidation potential, and we generally represent it like this: E Zn single line Zn2 positive. It is undergoing oxidation. Suppose the value is x volts. So if oxidation is occurring on the electrode, we call it oxidation potential. However, if reduction occurs, we call it reduction potential. So if I want to represent this oxidation potential in terms of reduction, I can do that. I can write E Zn2 positive single line Zn. When I'm writing like this, that means Zn2 positive is getting converted to Zn. That means it is undergoing reduction. In that case, the sign of x will get changed. I will write minus x volts. So if oxidation occurs, it is oxidation potential, and if reduction occurs, it is reduction potential. And we can express them in different ways also. Any element on which oxidation is occurring, if you want to write it down in terms of reduction, simply change its sign and you can write it down in terms of reduction. One more thing, if the oxidation or the reduction is occurring at standard conditions, standard temperature and pressure, that is 298 Kelvin and 1 atmospheric pressure, in that case, you call it standard electrode potential, standard oxidation potential or standard reduction potential. The only thing which you have to do is to put a naught sign on top of E, that is E naught, that means under standard condition. So standard electrode potential, standard oxidation potential and standard reduction potential. So this is what electrode potential is. Now the question comes to our mind, how to calculate this electrode potential? Well, the electrode potential of an electrode can be calculated by using standard electrode, and we have different type of standard electrode like standard hydrogen electrode, standard chlorine electrode, calomel electrode. In your syllabus it is given standard hydrogen electrode, so I'll tell you what is standard hydrogen electrode. But we'll not do that standard hydrogen electrode in today's class. We'll be doing that in the next class. I'll tell you the agenda for the next class. In next class we'll do standard hydrogen electrode, how it functions. We'll see Nernst equation, that is the dependency of EMF on temperature and concentration. We'll be doing some numericals on that, and we'll be doing resting. And means after that, we'll be doing some electrochemical cells. That we'll do from PPT only. So this is all about this class. But before ending this class, I would just like to request you one thing. Please subscribe this channel and please press that bell icon so that you can get all the notifications. Thank you very much. Thanks a lot for joining this class.